Good afternoon. I'm David Chappell. Welcome to this talk on data on Azure, the big picture. So here's the thing. This is really the big picture. I'm going to try to walk through just about every data service on Azure in 75 minutes. So what does that mean? It means that we have no time to waste. Let's get started, okay? We are talking about the Azure Data Platform. By data platform, what I mean, at least, is an integrated group of services, technologies, that lets us work with all kinds of data in useful ways. Great. Now, thinking about data is, in fact, thinking about this big, broad space. And so, I don't know about you, but I can almost never think about big, broad things without categories, without structure. And so I'm going to divide this space into three big categories. I would argue that we can think about data services by the kind of data they work with. And the kind of data we work with can be grouped into these three big categories. Category number one, operational data. This is read-write data. We read it, we write it. And it's really, in some sense, the data. It's where data begins. It's data applications use, like records in a CRM system, orders in an online ordering system. It's the birth of data. People then realized that it was useful to keep old versions of this data and use it for analysis. That gave rise to category number two, analytical data, which is read-only, typically, and it's used for analysis. This is classic data warehousing. This is also, more recently, the kind of data we use for machine learning, all kinds of analysis. Category number three, most recent of all, is streaming data. Data in which, if you don't process it quickly, like really quickly, it loses a large share of its data, of its value, excuse me. The canonical example of streaming data today is, of course, IoT data, like data from sensors. And so I'm going to divide the Microsoft Azure Data Platform into these three categories. It's a useful way, not the only way, of course, but I think a useful way to think about these different technologies. And darn, they are confusing. There are so many of them. Some of them overlap in some ways. There's all sorts of ways to get confused. So the more structure we have, the better. In the operational category, you have things like SQL Database, a relational database service. You have tables, you have HBase, you have, most recently, Cosmos DB. For analytical data, there's tons of stuff. There's SQL Data Warehouse. There's Data Lake Analytics and Data Lake Store. There's Hive and Spark, and that ... means a bunch more. All the Hadoop technologies, the Spark technologies. I'll describe these later on. There's machine learning. There's Azure Data Factory. And by the way, putting Data Factory in that category doesn't fit very well. It kind of spans everything. So not everything really fits in these three buckets. But I'm putting it there now just for simplicity. In the streaming category, the Azure services include Stream Analytics, Storm and Spark Streaming and Kafka, Event Hubs, and IoT Hub. We're going to walk through all of this at a high level in the next 73 minutes. Okay? Before we do, notice one thing about this slide. You might notice that in the middle, I'm lumping stuff together. I have multiple technologies inside a box. The reason for that is that all of those things are part of this larger thing called HDInsight. HDInsight is a suite of technologies based on open source offerings that Microsoft offers on Azure. They all have some technical commonalities, and they work together quite well. I'll describe those more later on. But HDInsight is this group of things that spans all of those categories. Okay? So I combined them here to help them fit better inside my HDInsight box. So let's start with some general observations about all of these services. The most important thing to say is this: these are all PaaS services. They're all managed for you. They all provide the benefits of PaaS. This whole talk is about these kinds of Microsoft managed services. Turns out that these kinds of technologies provide some really important and quite common benefits. You need not install anything. You can just use them. They're updated for you automatically. You might think, well, okay, updating. How important is that? Did you notice this yesterday? That the CEO of Equifax lost his job because some IT guy did not apply the Apache Struts update that should have applied? Updates are really important. As it affects the CEOs of our organizations, they'll get even more important. I can imagine a world where the CEOs who run our organizations require us to use PaaS services solely to avoid the kind of problem that just made this guy lose his job. They don't trust us anymore. Our mistakes cost them large amounts of money. So having updates done automatically is an important thing. It's worthwhile. Obviously, so is pay-as-you-go pricing, pay for what you use. Built-in high availability, replication in the cloud, and fast and easy scaling up and down. Those things apply to pretty much all the things I'll discuss today. And so I'm not going to reiterate those over and over and over. But keep that in mind. It's an important thing to understand about all of these data services. In fact, I would argue strongly that this is the future of how we do data in the cloud, obviously, and more broadly, the future of how we do data. On Monday, after the keynote, I was having lunch, and I sat down randomly in the show floor, whatever, and I was a nice guy sitting with me. We were talking about this. He was an IT admin. We were talking about this, and he said, you know, I just don't believe in this cloud stuff. It's Microsoft's vision, but it's not going to happen in my company. Never going to happen in this cloud stuff. And I was really surprised. I was so surprised because it's been a long time since I've talked to anybody who had that perspective. I'm curious. Do you often, who in the room, often talks to people who think the cloud is just, you know, kind of a fad, not the future of our industry as I do? Do you often talk to folks like that? Think the cloud is really not a happening thing? Some of you do, okay. Most of you do not, however. Well, those people are wrong, aren't they? They're wrong, like it or not. So, let's go on. We're going to start with operational data. And by the way, I mean no criticism of this guy I had lunch with. He was a fine person. I just think he was wrong on this issue. So, operational data, the leftmost column of our table. Operational data has its roots, at least its quasi-modern roots, in relational databases. So unsurprisingly, the first thing we're discussing here is a relational database service called SQL Database. It is easy as pie to understand. Applications send SQL queries, get back rows and columns. It's a relational database service. Very straightforward. Super. Why would you use this? Well, I've already told you a bunch of reasons why. It's PaaS. The benefits of PaaS all accrue to this relational database service. Also, it's got some other interesting capabilities. Microsoft is doing their best to make this an intelligent service. So it does things like monitoring your performance and adjusting. It does things like watching for security challenges and other things. Building intelligence into the database to catch those things, to fix those things, is an important part of the direction, the reality of the future for this technology. It also supports multiple database technologies today. This guy, for the longest time, was all about SQL Server. It was based on SQL Server. That's what it did. It provides most of the surface area of SQL Server. Today, however, it also supports MySQL and PostgreSQL. Microsoft understands that the future is much more than just its homegrown technologies. And so you're seeing support added for things like this. And it also has some interesting features for very specific scenarios. Anybody here in ISV? Anybody build SaaS applications? Oh, some of you do, right. So for ISVs, they often want to be able to have a separate database for each customer, okay? And you want to have great performance for all those databases. So if you want to, you can pay the amount this thing requires to get the best performance for all those databases. You're free to do that. But you're also free to use this thing called elastic pools that lets you pay a fixed amount for the total performance and then spread that across your customer databases. It's a way to more economically get good performance for ISV applications. Another quite specialized scenario, not specialized, specific scenario, that was just announced on Monday is this technology's support for managed instances. The idea is this. The idea is that SQL Database, naturally, is a service. It's a big service. Well, managed instances gives you an actual instance of SQL Server that is managed for you. Why is that useful? Because the managed instance gives you the full surface area of SQL Server. If there's stuff you really need, there's not much, but there might be, that's not in SQL Database, you can use this instead, such as in a lift and shift scenario like this one. You can put relational data and a managed instance in SQL Database, move your app, and it works just the same as on-prem. So it's not just SQL Database in a VM. It's a managed instance handled for you by the platform. There's also, as you probably saw in the keynote earlier this week, there's a new service from Microsoft, the Database Migration Service, that's designed to help you migrate on-prem data into SQL Database, not just managed instance, all kinds of things in SQL Database. So, SQL Database is Microsoft's core operational relational data store in the cloud, in Azure. But relational data stores are not the only game in town. People increasingly use NoSQL for operational data. Why do they do this? There are a few big reasons. The biggest one in my experience tends to be scale. People want more scale. And so, the pro of NoSQL databases is they can scale, typically, more and more easily than relational databases. Is there a con there? Sure there is. This is engineering, people. Engineering's all about pros and cons, trade-offs. Right? There are no perfect solutions. So what do you get? What do you lose, more correctly, when you go to these massive scale NoSQL databases? One thing you commonly lose is the ability to do transactions that span your entire database environment. And the reason is that NoSQL systems scale by sharding, breaking up data and spreading it across different servers. Doing a transaction, a classic atomic acid transaction, across multiple servers is challenging. So transactional behavior isn't the same in NoSQL systems, typically, as in relational systems. What else? You get more flexibility. NoSQL systems typically have no schema. You can just drop stuff in as you see fit, which is kind of cool. It's kind of useful. Except it's also kind of problematic because schema can be your friend. Schema can help you prevent errors, putting a char value in an int field, for example. So again, trade-offs. More flexibility, but perhaps a bit more risk. And finally, you get different data models. You're not locked into the relational structure. Now, what's good about that? That's good because the growth area for data today is not relational. The big growth in data is things like sensor data and click streams and so on, which are just not born as tables. And so with NoSQL stores, you don't need to actually put this stuff in tabular form. You can just store it as it is and process it. Cool. Very cool. What's the con here? The con is that the data models are maybe not as familiar to most of us as the classic relational SQL query model. All right? So what does Azure do for operational data about NoSQL? Let's walk through the offerings. There are 4 models that have become popular in the industry, and Azure supports all of them. I'll show you how in a minute. There's this notion of a key value store, where you provide a key and you get back some set of values. It's incredibly simple. It's almost like a hash table, where you just provide a value and get back data with that value. Simple. There's column family stores. Column family stores are not so simple. The basic idea is that, as the name suggests, you have tables, regular old tables, that have columns, but those columns are grouped into families. And typically you can do things like add new columns on the fly. They don't have a defined schema in that way. So there's flexibility there. We'll discuss an example in just a minute. There's document data stores, which store typically JSON documents. with no real schema, no defined structure. All kinds of diversity is allowed inside your document. And there are graph data stores that store data, unsurprisingly, as graphs, nodes and edges. Okay? On Azure, key value stores were implemented originally by tables. Tables are among the oldest things in Azure. They were in the original release back in, what, 2009, before the GA? Been there a long time. Tables are a key value store. Provide a key, get back some values. Life is simple. Why would you ever use tables? Well, because they're really simple. Right? They're really straightforward. They're really scalable. They can be very big, and they are almost unbelievably cheap. So if you want simple access to vast amounts of data for not much money, that has historically been a scenario for Azure tables, also called table storage. They use both those terms. Okay? What if you want column family store? Well, that's HDInsight HBase. Again, this is part of HDInsight. I'll show you what that means later on. But from a straightforward point of view, you make a request of your data and you get back the results. I'm not going to talk in any detail about the HBase data model because it's a bit non-trivial. But the idea, again, is that it's a good thing to use if you're using other HDInsight technologies. I'll show you later why that's true. I'll show you later why there's this technology and pricing connection across all of HDInsight. So it makes sense if you're using this one, use that one as well. I'll show you that later, what that's about. It supports incredibly big tables. I mean, amazingly big tables with millions of columns and billions of rows. In fact, the root of HBase is a paper published by Google, like a while ago, 15 years ago, describing their internal technology, which was called Bigtable. Good name, right? This allows really big tables, and it allows really sparse tables. So having a giant table with just a few points of data here and there is not inefficient. Those are some classic HBase scenarios. Next, kind of a digression, more correctly, a history lesson. DocumentDB. A couple of years ago, Microsoft released a document store called DocumentDB. They defined a language for it called DocumentDB SQL, in which you could query the database and get back your JSON documents. Now, don't be confused. DocumentDB SQL is not SQL. It's an extended subset of SQL designed for document-based queries. All right? There are no joins, for example. So it's not SQL, it's SQL-like. Great. DocumentDB was a cool technology. But DocumentDB today is no more, because DocumentDB has been superseded by our last topic in this section, Cosmos DB. To understand Cosmos DB, think about this. Think first about, well, gee, there are these different data models, right? There's key value store, and there's column family, and there's documents, and there's graph. How come I have to have a different technology for each one of these? Why can't I just have some standard way to support the data and project it out into each of these different approaches based on how I want to use it? Well, that's what Cosmos DB does. Cosmos DB, which grew out of DocumentDB, lets you expose data via the Azure Tables API, the key value store. It will, they tell us, let you access exposed data through column family API. They've not told us exactly which one yet or when, but they've said it's going to come. It also supports the DocumentDB SQL API, no surprise, it grew out of DocumentDB, plus it supports the API from MongoDB. Mongo, as you might know, is a popular open source document database. And finally, they also give you support for this thing called Gremlin, a popular graph API. So you can store your data in Cosmos DB and view it through any of the popular NoSQL models. You can't quite use column family yet, but it's coming, they tell us. Okay? Interesting idea. What else is interesting about Cosmos DB? Why would you use Cosmos DB? Well, it's big. It runs all around the world. You can move your data around the world. It will sync it for you. It has low latency access from around the world. If you want to build a very big app, it's a great choice because it's a very big database. It also has multiple consistency options. I'm going to stop here for a second. What does this mean? I told you earlier that in NoSQL systems, you commonly have data spread across many machines. It's replicated. You typically store the same data more than once across different machines. Cool. It allows scale. It allows fast access. But it also means there's a problem. Because if I've got this multiple copies of the same data item across different machines, what happens on an update? Somebody goes to one of them and writes it, okay, and that change, that write, will propagate over time other copies, right? But suppose someone else comes in and reads that data while the write is propagating. They might get old data, right? How do you deal with this? Well, traditionally, a database like this would simply choose an option and go with it. Cosmos doesn't do that. Cosmos DB gives you a bunch of options for consistency. One option is what's called strong, which means when I do a write on something, that change will propagate to all the copies, and no reader will see anything until that change is done. Guaranteed consistent. It also supports what's called eventual consistency, which means when I do a write on something, doesn't matter at all. A reader might well see the old data when they come in. It'll be consistent eventually, but not right now. Those are the most common options we've seen in technologies beforehand. This guy also supports others, one called Session, for example. Session lets you see your own writes, but others might see inconsistencies. And there's a bunch more, actually. There's a bunch more. Turns out that most people who use this do not use either strong or eventual. They use one of the immediate ones. So those are all built into Cosmos DB. They were mostly in Document DB as well. This thing also has 99% SLAs for a bunch of things. This is the beginning of a theme because Microsoft thinks that SLAs are really important on these services. So we're going to see this a lot. What's interesting, though, is the SLAs don't cover just the usual stuff we're used to, like availability. They cover things like throughput and latency. That's amazing. Latency is a fancy word for delay, right? And so what they're telling you in the SLA is that when you do a read, you are guaranteed that 99% of your reads will return in less than 10 milliseconds. Nobody else does that. That's really interesting. I admire their confidence. And there's also one for consistency, guaranteeing that those rules are followed. So, really strong SLAs. Going forward, it's fair to assume that Cosmos DB becomes the main NoSQL alternative to SQL Database on Azure for operational data. And one more thing. If you want to, you're always free to just create a bunch of ordinary IaaS VMs on Azure and move your stuff into them. You can do that. You can move operational relational databases, like SQL Server if you want, clearly, but also Oracle and MySQL and SAP HANA. You know, Azure has giant VMs that are almost designed to run SAP HANA because HANA is this in-memory database that wants massive storage in memory. So there are VMs on Azure designed to support things like that. You can also run NoSQL databases up there. You can run MongoDB. You can run Neo4j, which is a popular graph database. So, to my mind, those should generally be transitional stories. New stuff ought to go into data services, but you can do this if you want to. All right, on to category 2, analytical data. We're going to be here for a while because there's a lot of stuff to talk about in this space. So, before I do anything, I want to talk just quickly about this thing that isn't even on my chart. Microsoft sometimes categorizes this as storage, not data, which frankly confuses me. Azure Blobs. Blobs are incredibly simple. The acronym stands for Binary Large Object, and in general, this category of data storage is called object storage. It's like Amazon's S3. So the notion is you can send requests and get back binary data. This thing is all about storing binary data. Why would you use blobs? Well, there's a lot of very good reasons. They can store basically anything. Images, code, whatever you like. And blobs also have these options called cool storage and archive storage. You know, if I were being complete, my 3-column model of operational, analytical, and streaming would have a 4th column at least for archive data. Archiving is its own world. And in the Azure environment, the archiving story now is those options in blobs. They're also very scalable, and they're really cheap. So blobs turn out to be a very good way to store all kinds of stuff. And you're going to see them used in my scenarios in just a few minutes. They aren't purely analytical, of course, but they're in this section that are going to appear in scenarios in just a minute. So let's start once again with technologies in Azure for handling analytical data that is relational. And the main story there is SQL Data Warehouse. As the name suggests, SQL Data Warehouse stores relational data. It's a data warehouse. But it's designed to store lots and lots and lots of relational data spread across all kinds of machines. And you can scale this as you wish. Then, SQL Data Warehouse, from various clients like Power BI or Excel or Tableau, lets you submit queries, Transact SQL queries that run in parallel. If I have huge amounts of data that I want to analyze, if I run queries where there's a single instance running, it will probably finish someday before I die, right? If you want to get these things done in a reasonable amount of time, you've got to run the queries in parallel. And so that's what happens here. This technology runs queries in parallel across parallelized data. So both data and query are spread across multiple systems to make it much faster. Okay? We're going to see that same theme over and over in this section. Now, how about this? What if your query wants to access not just relational data, but also unstructured data in blobs or in this thing called Azure Data Lake Store? Quickly, Data Lake Store is a lot like blobs, but it's different in some important ways. What are those ways? I'll tell you later. Okay? We'll get there. But for now, think of it as more or less like blobs. It stores unstructured data. If I want to build a query here that accesses binary data, I can do that because there's this technology called Polybase that lets you reach out to those guys and have them be part of your query as well. So, SQL Data Warehouse in a very small nutshell. It lets you store large amounts of relational data and run parallel queries across that data. It lets you, if you wish, reach out to unstructured data through this thing called Polybase. Oh, and by the way, in case you've never seen it, Power BI looks like this. Power BI is a tool for visualizing data, doing things like that. But just in case you're brand new to this space, I wanted to show you a sense of what it looks like. So why would you use SQL Data Warehouse? Well, as I've implied, it's really scalable. It's a data warehouse. It'll store large amounts of stuff. And here, it'll store petabytes of data. It's got all these massive Azure resources to deal with. So huge scale. And as I said, the queries are parallel more correctly. They use what's called massively parallel processing, MPP. This guy also separates compute and storage. This is really interesting. You can scale both the storage part and the compute part independently, and you can scale them with sliders. On the website, you just slide things back and forth to get more parallelism in your compute or less, to get more data storage or less, which is very interesting, I think. You can shut down the compute, pause it, and pay just for storage. Well, that's a good thing. Makes sense. And it has an SLA. Again, Microsoft is big on this. Stop for a second here. In the old world, in the on-premises world, vendors all strove, is that a word? All tried hard to build reliable software, right? If you installed things and they crashed all the time with internal bugs, you were not happy. Well, in the modern cloud world, the analog to that is SLAs. These are services, not software that you buy and install. And so just as you would care deeply about the reliability of on-prem software, you ought to care deeply about SLAs. And so Microsoft, as a major focus throughout this set of technologies and others, is putting SLAs on things. They're proud of the fact that this technology has a 99% SLA for availability, and Amazon Redshift, its most visible competitor, has no SLA. So, make of that what you will. Having data in a data warehouse means it's available for analysis. You then, of course, want to analyze it with something. In Azure, the relational analysis technology to use is analysis services. This guy uses the same tabular data models from SQL Server analysis services, the classic database, okay? You can, once again, invoke queries from various clients, and analysis services can access data in lots of places. SQL Database, SQL Data Warehouse, obviously, blobs, those are all cloud sources. It can also reach out on premises and talk to SQL Server or Oracle or Teradata or whatever. So, why would you use this? Well, it's based on SQL Server. It's based on the engine in SQL Server Analysis Services. And as I mentioned, it can share tabular models. Like everything else in the cloud, you've got these expandable cloud resources and thus high performance, and you can stand up an analysis service instance in a couple of minutes, unlike the on-prem world where you install this and do all that stuff, right? And as we just saw, it connects with lots of clients, lots of data sources. Here's a scenario. Let's walk through a more complete scenario that ties these things together. Suppose you've got some e-commerce app that your organization has built, and it's chosen to use SQL Database as its database, relational. You can then periodically dump data into Data Warehouse. This is just classic extract, transform, load. Classic ETL. This is just the same stuff people do today in the cloud. You can then analyze that with analysis services, and your people, business analysts, whatever, can access this with Power BI or something else. So these things fit together in much the same way they do on premises. The difference is they're now cloud services with all the benefits that brings. I have another question. Data in the cloud. I've given, in the last 8-9 years, something like 10,000 talks about cloud computing. Something like that, some big number, okay? And back in the early days, people were always saying, oh, I can't trust my data in the cloud. I can't possibly do that. Now, when I talk to CIOs especially, almost all of them say, you know, my data is safer with big vendors like Microsoft than it is on premises. I'm curious, who here works for a company where you believe your leadership, maybe that's you, thinks that their data is more secure inside their organization? Who thinks that today? They're all sitting over here, apparently, right? So a few of you, okay. Do you guys work for government organizations? Yeah, okay. If you're the NSA, if you're the military, different conversation, okay? Who here is non-governmental, okay, not one of those very secure places, and believes this, believes their data is more secure in their own environment? I only see a couple hands now. Pardon me? Do your leaders believe? Do your leaders believe this, right? More of you, a few of you, but a small minority here actually in the group. I think that's progress. I think that's really a good thing. All right, speaking of on-premises and cloud, you can take this same scenario and you can add on-premises data. Maybe it's the case, for example, that you want to have some operational data from SQL Server on-prem be dumped into the data warehouse in the cloud. That's fine. Maybe you want to use a tabular model analysis services that you got from on-prem. That's fine. Maybe you want to report from reporting services on-prem to be part of what Power BI shows people. That's fine too. So recognize that these are not pure cloud scenarios. You need not live solely in the cloud if you adopt these. They're also designed to be used in combination with existing or new on-premises things. All right, so that's the story for relational analysis in the cloud. Just as in the last section, I began with relational operational data, and I went to NoSQL operational data. Great. So now let's go to non-relational, unstructured analysis in the cloud. And that story probably needs to start with Hadoop. Because Hadoop is an open source technology that now has a whole bunch of things in it that is the genesis of one of the core technologies in Azure for doing this kind of unstructured data analysis. It's called HDInsight. The HD comes from Hadoop, if you're wondering where that is. This began as Hadoop in the cloud. It's now a lot more, in part because what was Hadoop has become a lot more, as we'll see. So here's the idea. You know that all of this stuff runs on physical servers in Microsoft Azure data centers, right? You also know that things actually run in virtual machines, running on those physical servers. If you want to use HDInsight on Azure, you need to create a defined HDInsight cluster, which you can do from the portal, the Azure portal. You create some number of VMs which are in your HDInsight cluster. And by the way, you pay for these. As long as they're running like any other VMs, you're paying for them. All right? Now, what HDInsight does is it takes that cluster of VMs, it makes them all able to access storage via this thing called the Hadoop Distributed File System, HDFS. Now, originally, HDFS was implemented on premises, like Hadoop itself. And so originally, HDFS was all about using physical servers on-prem to spread data around. In the cloud, however, on Azure, HDFS is an API in this context. The actual data used by things that use HDInsight is stored in blobs or in Data Lake Store. Both those are supported. Then, on top of your HDInsight cluster, you can use the technologies that come with Hadoop or, increasingly, those that come with Spark. Hadoop and Spark are both open source. They both run on a cluster. They both use HDFS. What happened here was Hadoop was built first. Then the guys who built Spark, which is Hadoop-like, as we'll see, but better in some ways, decided to just adopt the Hadoop cluster in HDFS and build cool stuff on top of it. That's why Spark runs on top of this. So HDInsight, the Azure service, includes all of these things. You get a sense here of why, if you use one HDInsight technology, the other one makes sense? You're paying for that cluster all the time, and they all use this cluster you're creating. They're a group of things. So Hadoop, for example, includes technologies across all three categories I've been discussing here today. There's HBase we saw earlier, which is operational, but it runs on the cluster. In the analytical space, there's Hive and Pig, which are languages for creating parallel queries, effectively, with technologies like TES and MapReduce, and this newest one, LLAP. What does LLAP stand for, you're wondering? It officially stands for Low Latency Analytical Processing. But of course, it came from some university, so the guys who named it originally called it Live Long and Process, which I thought was great. I like that a lot. And for streaming, there's a bunch of things. There's Storm, there's Kafka. So, HDInsight includes technologies derived from the Hadoop family that all run on a Hadoop cluster, an HDInsight cluster, excuse me. Let's look at these a little bit. The big idea here is that I can have, in blobs or Data Lake Store, large amounts of unstructured data spread across multiple systems. I've got lots of data. To analyze that data in something like human time, I've got to run my query in parallel. right? So how do I do that? Well, Hive is a common language in the Hadoop world to generate these parallel queries. They then run using MapReduce or TES or LLAP. But do you see a theme here again? Parallel data, parallel queries? Yeah, that's like data warehouse, isn't it? Except this is for unstructured data. It's a very similar architectural pattern, but it's being done on different kinds of data. Great. Why would you use this? Well, it's really scalable, right? Can hold really large amounts, petabytes of data, and the queries run in parallel, as I just showed you here. It also, this is interesting, it's open source, right? It's open source. What that means is, if you write code on this system, that code can move elsewhere, on-prem, other cloud platforms, because everyone supports this stuff. That's interesting. It also means, if you're a developer, that the skills you learn here are portable as well. The skills can be applied in lots of places. So that can be a big win. The fact that it's open source and available in lots of systems can be valuable for you as a technology professional. It also provides, of course, an SLA. Now, Amazon's competitor is called EMR. It was called Elastic MapReduce after its origins in Hadoop, but now it's just called EMR because they support lots of stuff, just like HDInsight. But Amazon has no SLA. So Microsoft, again, is big on this. They're big on this notion that what they're doing is reliable, and they will promise it's reliable by giving you an SLA. But here's what's happened. This thing called Spark was built by some guys at University of California, Berkeley, a while ago. And it was Hadoop-like. It was built, in fact, on the same cluster, the same file system, HDFS. But it does different things. It focuses on analytical data and streaming data. And it does a lot more in memory. Because it uses these things you can see here. Oops, sorry. These things called resilient distributed data sets, which live in memory and let the various parts of the system work together, share data more efficiently. So today, it's fair to say that Spark has more mindshare. People are more using Spark for new projects than the older Hadoop stuff. Okay? You can use what you want, of course. They're all supported. But it's fair to say that Spark has more mindshare. Why use Spark? It's faster. That's one big reason. It's also better integrated across pieces, as we'll see a bit more later on in the talk. Again, it's open source. So just like the Hadoop stuff, your code and your skills are more portable. And once again, yep, there's an SLA, part of HDInsight. I have been talking about Data Lake Store. Let me stop for a second. You guys look just bludgeoned, right? I'm going really fast over a lot of stuff because I was asked to cover the whole platform in 75 minutes. So the goal was to give you what and why about everything. No how, just what and why and how they fit together. How are we doing here? Do you feel overwhelmed? No, we're okay? And worse yet, we're doing it over lunchtime. Right? So, yeah, so thank you for coming and for sticking around. Right. I've been talking about Data Lake Store, but not said much about it. Well, it stores unstructured data, but look at this. You access it via this thing called Web HDFS because Data Lake Store is HDFS as a service. Blobs are blobs. They have their own API, their own environment. This guy is the Hadoop distributed file system as a service. That's why it's not like blobs, at least one of the big reasons. Why? Why would you use this? Well, it's a bunch of reasons here. As I just said, it's HDFS as a service, and HDFS is becoming the default storage mechanism for data lakes. What's a data lake? No one agrees. But I would suggest it just means this place you can drop data into without worrying about its format or anything else. You know, in SQL Data Warehouse, it wants tables. It's relational, okay? A data lake like this just says, give me your huddle data, you're in breathe free, whatever. Whatever you have, I'll take it. Just put it there in whatever form you like. So HDFS is good for that. It's becoming the default for how people do this. Not just Microsoft, just in the industry. It's got the standard API defined by Apache, which Data Lake Store exposes. And here's the key thing. Data Lake Store, unlike blobs, is optimized for analytical workloads. It's meant to be accessed in parallel because you've seen that parallel compute is essential to get performance out of these analytical problems, and it can be really scalable. A single HDFS file can be a petabyte. That's way more. That's way more than blobs. They can be really big. So either one can be used, and you saw both of them sit below the HDFS API in HDInsight. But here, this guy is designed to be used with parallel query, where blobs were not. Blobs are also, by the way, one of the original Azure technologies from 2009, a long time ago. Now, to make things even more complicated, on top of Data Lake Store, which is here in the bottom, you see, Microsoft also provides a service called Data Lake Analytics. Now, what does that do? It's not part of HDInsight. Actually, in the branding, it might be. I don't know. But it's not part of the Hadoop cluster business. It's its own world, okay? Doesn't run on a Hadoop cluster, nothing like that. Great. Instead, what this guy does is, yes, that's right, it does parallel compute. You can give it a query to do analysis across very big chunks of data, and it will break it up, run it in parallel, so it's done fairly quickly. It gives you a Microsoft-defined language to do this, however, called USQL. So once again, it's that same pattern we saw before, but now expressed in a Microsoft-defined technology, not one that came from the open source world, like the Hadoop and Spark things, right? Why would you use this guy? Well, it runs queries in parallel. You can just easily specify how much parallelism you want. Straightforward to do. Okay, that's great. It's got this language based on SQL and C#, which is USQL, which is interesting to use. And also, you don't have to have a cluster. Remember HDInsight? You've got this cluster that's always running, and you pay for those VMs. That's why once you have one technology using that cluster, you may as well use the others, because you're paying for those things anyway. Here, there's no cluster. Here, you tell it how much parallelism you want in your USQL query. It runs the query, spins up the compute resources, and shuts them down right away. It's kind of like being serverless, right? Kind of like Azure Functions. It's not open source, however, so the code and the skills are less portable. Options, trade-offs. Here's a scenario. Suppose you have customers with an e-commerce application built by your company, just like before, but now the app uses Cosmos DB. No SQL data, not a relational database underneath. How do you analyze that data? Well, we've seen the answer. I can dump that stuff in the Data Lake Store. Maybe I'm dumping in clickstream data. Maybe I'm periodically hoovering up the actual historical data from the operational database. I can then analyze that using, well, I got a lot of choices. HDInsight, the Hive, Spark options, Data Lake Analytics with USQL, got a bunch of options. I can present that to my analysts through Power BI again. You can see it's very analogous. Very similar things are happening. Operational data with no SQL structures this time. Big parallel data analysis happening with other technologies, this time on non-relational and structured data. And again, Power BI to show things. It's very analogous to the earlier scenario. All right. Take a deep breath, please. Because there is another kind of analysis that we do on all sorts of data that is becoming more and more important. And it's called machine learning. Actually, it's most often called artificial intelligence. But when people say AI these days, they almost always mean ML. So, machine learning. Machine learning can be hard to understand. Here comes the world's shortest machine learning tutorial, okay? So, it isn't hard at all. It's actually a very simple concept. I've got some data here. This is data about credit card transactions. What it shows is the person's name, the amount of their credit card charge, and whether or not it was fraudulent. Now, if we could find a pattern in this data, maybe we could use that pattern to predict whether some future credit card transaction is likely to be fraudulent and stop it right there at the cash register. That would be cool. So, Can you find a pattern in this data? Well, the answer is sure. It's obvious, right? If your name starts with P, you are a criminal. Right? Simple, straightforward, and deeply, deeply wrong. If patterns are easy to find in small amounts of data, they're probably going to be wrong, not predictive, not reliable. So how about this? Here is some more data. Now I have 10 records. Is there a pattern in there? Well, the answer is that there actually is one. You could probably find it if you look long enough. But how likely is it that a pattern you'd find in here, maybe it's the person's, I don't know, maybe the amounts are big enough and the card's issued in the USA and used in Japan, and the card holder is young or old, whatever. Maybe there's some pattern in there you can define. Could you find it? And if you did, would it be reliable? I've only got 10 records. But what if I have 10 million records or 10 billion records? Now, there probably is a pattern in there that will help me predict which credit card transactions are fraudulent. Finding that pattern is worth a lot of money. So I could hire a bunch of folks to look at the records themselves personally. That's not going to work. We can't do that. Software can do that. Software that does that finds patterns in data that let us predict future events, is called machine learning software. Right? Machine learning means finding patterns in data that you can recognize again and thus predict what's likely to happen. How does that process work? It looks like this. You start with raw data. You then have to apply pre-processing to that data with various pre-processing modules. Turns out that sounds simple, but the truth is that in most ML projects, you do this over and over and over and over and over. It commonly eats up 3/4 of the time, and people hate it because it's boring. But it's a big part of the time. Then once you have prepared data you're happy with, you start looking for patterns. And you do that by applying machine learning algorithms. Each run-through produces this thing called a model. It's kind of a weird name. A model is code. You can call a model. You could pass a model data, like data about a credit card transaction happening right now. It'll spit back to you the probability that it is, for example, fraudulent. You do this over and over and over as well to create your model. And by the way, in the jargon of machine learning, no one ever creates a model. I'm going to say create all the time. No, in machine learning, you train a model, right? Like it's a pet, right? You train a model. So I'm going to say create. Then you deploy your model, and applications can use it later on. I did all of this because I wanted to show you what Azure Machine Learning provides. That is the generic machine learning process, no matter what you're doing. Azure Machine Learning, the cloud-based tool in Azure, takes this process and provides several things. It provides a bunch of pre-processing modules for your data. It provides a bunch of machine learning algorithms for your training process. It provides this nice tool called ML Studio that gives you a graphic tool to wrangle and run through this whole process, do all these things. And it provides an API to let applications access your model. It also provides a very straightforward way to deploy your model in the cloud. And as of this week, they announced they also are supporting wrapping models inside Docker containers. I can now deploy models as Docker. So that's Azure Machine Learning in a nutshell. Why would you use this? It's got a lot of stuff. Lots of learning algorithms, lots of data cleansing tools. It gives you a bunch of useful stuff. It also gives you this nice graphical tool. And Microsoft today says that that tool is for what they call citizen data scientists, by which they mean non-professionals. Because here's what's happened. It seems that lots of pro data scientists already have their way of working, and it's based on code, not GUIs. So this tool is GUI-oriented, primarily. And so we'll discuss what's happening there in just a minute. So Azure also has this thing called the Data Sciences Virtual Machine in the marketplace, which provides a bunch of prepackaged stuff for pro data scientists, code-oriented things that you can use. Azure also, Microsoft also, this week announced the Azure Machine Learning Workbench. This is interesting. This is a code-based world designed for pro data scientists. It gives you this desktop environment. Stop for a moment. This thing is called the Azure Machine Learning Workbench, and it runs on your desktop. Don't be confused by that. Right? It's interesting, I think. That gives you the ability to do ML stuff alongside your favorite code editor. It supports a bunch of stuff. There are, for example, these very cool tools for data pre-processing. We saw a little bit of in the keynote that actually let you describe what you want data to look like, and it will go make it happen on large amounts of data. It's interesting. And this is also interesting. You can create models. You can train models. You can train those models by using your own desktop machine, but if you have lots of data, it'll take forever, right? Or you can train those models on a server you pass this off to, so it might take a while. Or you could train those models by passing the machine learning algorithm you're running onto a Spark cluster in HDInsight. So you have all those options to do training locally, to do it on a local server, do it on a cluster in Azure. So this thing is tied to Azure. It can be. It's not purely a desktop-oriented thing. It's hard to overstate how important machine learning has become. It's hard to overstate. It's also hard to overstate how hard it can seem for neophytes to get their mind around this space. Right? I hope I've helped with the basics here, but trust me, if you've not looked at this before, it gets much more complex very fast. Just be warned. All right, so I might use machine learning like this. Suppose I've got a bunch of credit card data, like I talked about earlier. It's in blobs, it's in something else. I can run that through Azure Machine Learning, iterate the data prep, iterate the model creation, model training. I get a model out the other end. I can then have a payment app living on premises somewhere. Credit card customers use that. They're trying to charge things. That payment app could actually call into a fraud check app that calls the model. Every credit card request that somebody makes could be checked through machine learning. This actually happens. Machine learning through a model to predict whether or not it's going to be a failure. Or fraud, rather. Common thing to do. Creating the models can be hard, but once they're available, using them is quite straightforward. Here's a more complex example. Suppose you are a mobile phone company. You're Verizon. I'm just making these up. They're not doing this. They actually might be, but I'm making this up. Right? You're Verizon. You're AT&T. You're T-Mobile. Whatever. Okay? You've got a call center. Your call center people have an application that they use. People call in, often unhappy, right? You call your company because you're unhappy. You'd very much like those call center people to know each caller's propensity to churn. That's jargon that means how likely they are to switch to another customer, not another carrier. Put more colloquially, it's a measure of how much they hate you. Right? You're trying to figure out, as a call center operator, who is this person? Because if they're likely to leave your company, you're authorized to give them better deals, probably. And you'd like to know that for each caller coming in. Can you do that? Well, maybe you can, because if you're a mobile phone company, you have all this data about everyone's calls. Can you find patterns in their data usage, their call structures, that help you predict who's happy and who's not? Very possibly. But here's the thing. The raw call data is probably too voluminous. It's probably too big. So you probably have to do something like this. You might run an HDInsight, Hive, or Spark job to aggregate that in some way. You might then decide that you want to add data about the customers from your CRM system. So perhaps you run a second Hive or Spark job to aggregate that into the data you actually want to use for machine learning. Again, the data prep parts of machine learning are the big time sink in so many projects. And once you have that data, you can now use Azure Machine Learning or the Workbench to create a model that predicts the customer's propensity to churn. How mad at you are they? You can then have the call center app use that model for every call to let the operator figure out what they can offer this customer. That could have a great deal of business value. And so we're seeing organizations more and more spend money to try to do things like that. But now here's the thing. If I build a model that predicts behavior based on call data, the world changes, doesn't it? What I have to do is I have to periodically rebuild and redeploy that whole thing. How often? Every week? Every month? Whatever. Reasonably often. You can automate that. You can automate that with Azure Data Factory. Data Factory is a tool designed to create all kinds of data integration pipelines. Sadly, for time reasons, that's all we're going to say about it in this talk. But it's very interesting. And the new version, now in public preview, also supports SSIS pipelines. You can run those guys up in the cloud. So it's like SSIS in the cloud, but now it's much more like it because it supports SSIS pipelines in Azure. One last thing here. I've discussed all these services in Azure for analytical data. Just as with operational data, you are free to create IaaS VMs and move existing on-prem analytical workloads into the cloud. You can do this for relational data. You can run SQL Server again, your MySQL Data Warehouses, SAP HANA, whatever you have. You can also use unstructured things. You can put your Cloudera or Hortonworks Hadoop cluster in Azure VMs in the cloud if you want to. So you're not forced to use these services. You can use just raw VMs and move your stuff up there. All right. 10 minutes left for streaming data. Streaming data is the last column here, and it's, again, increasingly important. Big growth here, largely due to IoT. So one option is the Microsoft-defined technology called Stream Analytics. This is interesting. What you do is you create this thing called a standing query in a language that is actually derived from T-SQL. You create a standing query that looks at a time window of the stream coming in, and it returns data that matches what your query asks for. If you're doing time-based queries, looking for things in certain windows in the stream, this is a good fit. Technology designed for problems like that. Another option for stream processing is Storm. You recall earlier, part of HDInsight, which means it runs on that cluster that you create, okay? So you get streams in a Storm application. They are processed initially by what are called spouts. Spouts create tuples, and tuples are processed by bolts. I love this terminology. Who are these people, right? I don't know. But so the spouts take it in, do some pre-processing, the tuples are fed into the bolts, and the bolts do things like maybe call an ML model or do more processing. And there exists in the open source world a whole bunch of spouts and bolts you can just grab and use. So, kind of funny. It's analogous to Stream Analytics, but it's more general. It's not just time-based. It's more general, more complex as well. Finally, there's Spark Streaming. Spark Streaming does something similar. It takes streams, it processes them, great. The big thing here is that Spark Streaming is part of the unified Spark environment. Storm was built after the rest of Hadoop, so it's its own world. It runs in the cluster, but it's its own world. Spark Streaming was built with Spark, and so it uses those RDDs. It shares things. So this guy's gotten more and more popular. As Spark has grown in popularity, so has Spark Streaming. To do streaming processing, however, you first have to get that data into your system. And how the heck do you do that? Well, you need technologies for ingesting events. And Azure provides several of these. Event Hubs is the generalized solution for ingesting events, useful for lots of scenarios. They support Kafka, which is part of the Hadoop Spark world. It runs in the cluster, right? So you can use Kafka, especially if you're using other HDInsight technologies. And they support their own thing called IoT Hub. This is like Event Hubs, except IoT Hub is designed, as the name suggests, for talking to devices. So it provides more than just event ingestion. It provides a way for devices to authenticate themselves. It provides routing. It provides two-way communication. You can talk back to the devices as well. So for pure IoT scenarios, that's likely your best choice. Here's a simple picture. Suppose I have a bunch of devices. Maybe they are refrigerators, and the devices are monitoring the temperature of all these industrial fridges. The events can come in from those devices, be handled by event hubs or Kafka or IoT hub based on your choice of other technologies and your exact problem. They can then be analyzed by any of the things I just talked about, Stream Analytics or Storm or Spark Streaming, and then be sent up to business users. So an alert, for example, might indicate that this fridge is getting too warm. Could be sent through all this and action could be taken. It's interesting. Microsoft provides all sorts of options here. And there is guidance when to use which one. But recognize these do similar things, as we've seen in the last section as well. And so you can choose the one that you think best fits your problem. One last thing here about streaming. There is this thing called the Lambda architecture. This has nothing to do with Amazon's Lambda serverless technology. It just reflects, in my experience, the trend toward giving cool names to really simple ideas. So here's the really simple idea. The simple idea is that you've got some data coming in, and you process that data with stream processing. We talked about this, right? Now the challenge here is that when you do this, you can get very quick responses, but they might turn out to be wrong. They might be inaccurate. Because maybe it's the case that you process this first 1,000 bits of data, and then 2,000 chunks later, something comes that changes this. So stream processing is really good for getting fast analysis of data, but it might not be accurate. So what do? What you typically do in this Lambda architecture is you also put this incoming data into your data lake, and you process that guy through a slower batch mechanism that gives you not as fast, but likely more accurate results. The Lambda architecture. Is this really so complex it needs its own name? I don't know. But anyway, on Azure, that might look like this. Devices coming in, as I just showed you, processed through an ingestion technology, a stream analysis technology, passed off to business users. I just showed you that. At the very same time, you can be dumping all those events in Data Lake Store and process them in a batch mode with the usual things, Data Lake Analytics, HDInsight, the Hive or Spark technologies, and pass those off more slowly to users. This is commonly done because just doing real-time analysis, while useful, probably isn't enough. So typically people will store incoming events in a data lake and process them later. And you can see why you need those massive parallel processing mechanisms, because there are huge numbers of events potentially, lots and lots of data. So let's end here. I have 5 minutes. I think this is worthwhile. I have talked about Microsoft's technologies across a whole range of areas here. But they aren't alone. And I want to make sure you understand. Some of you may have some background in the Amazon world or the Google world or both. And so to make sure that if you have that, you can map it. We're talking about, you can map that to what I've been talking about today. Let me just show you a chart that illustrates the corresponding broadly analogous technologies across different cloud platforms. I'm going to show you Azure, Amazon, and Google. Now realize, I'm not suggesting by this chart these are all equivalent. Microsoft, for example, has SLAs across many of these, as we saw, which Amazon does not. There are various pros and cons. I only want to show you what fits in the box, so you have some sense of what competes against what. And if you've heard about Amazon things, for example, you know which Microsoft technology fits in that same box. So in the Microsoft world, as we've seen, there's SQL Database for relational operational data, and there's Cosmos DB and a few others, but Cosmos is the direction for NoSQL. Analytical data for data warehousing, there's Data Warehouse for relational and Data Lake for unstructured data. Hadoop and Spark are in HDInsight. Machine learning is Azure Machine Learning. And then stream processing, various choices, stream analytics, Storm, Spark Streaming. And for data ingestion, there's Event Hubs, there's Kafka, there's IoT Hub. This is a summary of this whole session, that line. AWS, Amazon Web Services, has analogous things. RDS, although RDS is more like managed instance than like SQL Database. RDS gives you your own managed instance of a database server, not a big service. So it's not exactly the same, but it fits in the same box. DynamoDB, a competitor to Cosmos DB. For data warehousing, they have Redshift for relational data warehousing. They don't currently, to my knowledge, have an analogous technology to Data Lake, HDFS as a service. Hadoop Spark, that's called EMR, their technology. Amazon Machine Learning. Amazon Machine Learning is actually quite different from Azure Machine Learning. It's designed for developers. And so it assumes you know virtually nothing about machine learning. It's very, very simple, which has pros and cons. It's really simple. You can't do all that much, but it's really simple, so anybody can use it. Pros and cons. Stream processing, they have Kinesis, their main story here. They also support Spark Streaming. For ingestion, they've got more Kinesis, Streams, and Firehose. They support Kafka. Those open source things are supported pretty widely. For Google, they have Cloud SQL and Cloud Spanner. Their Cloud Data Store, you can see here, BigQuery, Cloud Data Proc. Their machine learning is called Cloud Machine Learning, no surprise. Cloud Data Flow, and again, they support Spark Streaming. And for ingestion, they've got Cloud Pub Sub. So again, don't take this to mean that these are all equivalent to all the same features, because they're not. Rather, the intent is just to show you how these guys correspond and give you a sense of which other technologies out there, which of the cloud services are analogous to those we talked about here this afternoon. And with that, we're back to the first idea. A data platform as an integrated group of technologies that lets us work with all kinds of data in useful ways. I hope that I have shown you the way in which Azure supports that. Because, of course, we know the goal is to address whatever needs your organization might have. Thank you very much.